Hello everyone. Today I'm going to present to you our paper, Modeling Updates of Scholarly Web Pages using archive data. My name is Jayawardana and I'm from the Web Science and Digital Libraries Group at Old Dominion University. So if you think about the web, the size of the web in particular, it's massive. So as of November 22nd, the web has 5.45 billion pages out there. So if you take a small crawling infrastructure, it's very challenging for something like that to crawl the entire web. It's near impossible. On the other hand, it's more feasible to crawl just a portion of the web. For instance, if you're building a search engine that indexes publications, something like CiteSeer, it's much more feasible to do with small hardware. On the other hand, it's even challenging to crawl a large number of URLs, regardless of whether it's a focus crawl or not. So the problems that you may encounter when doing that is the crawler may not finish visiting all web pages before they change. So when the crawler revisits the web page, it may have already changed once, twice, or even more. And on the other extreme, the crawler may revisit web pages that have not changed yet. So this is a waste of resources and bandwidth. You should only ideally be crawling pages that have changed in order to gain a meaningful update to your search index. So what we can do here, can we select and prioritize a subset of URLs based on how likely they are to change? So in order to do that, you need information of how the pages changed and evolved in the past to make a prediction of how it would change in the future. So one resource that you could use that's openly available for the public is web archives. So in this research, we used archive data from the Internet Archive to do this estimation for how likely pages are to change. And from that estimation, we ran a simulated crawl scheduling test and checked how good of an estimation that we obtained from the Internet Archive. And does it improve on the crawl scheduling methods out there? So the key contributions from this research is that first we studied the dynamics of the scholarly web using archive data from the Indian Archive for a sample of 19,977 author websites. Next, we verified that these updates follow a near Poisson distribution. Next, we developed history-aware crawl scheduler, or HACS, which uses archive data to find and schedule a subset of seed URLs based on their likeliness to change. Finally, we compared our HACS model against several baseline models in a simulated web crawling task and demonstrated that it provides better estimations. So we started with a dataset that contained Google Scholar profiles of authors. We initially had 396,423 of those profiles. But out of these profiles, only 139,910 profiles had a homepage URL link in them. So initially we selected those profiles because we needed homepage URLs as seed URLs to start with. Next, when we did some analysis on these URLs, we found that a portion of these URLs pointed to organizational websites. We chose URLs with a tile in them to just select URLs that are hosted within a directory, and we obtained 24,236 URLs from that. Next, we used these URLs and sent them to the Internet Archive using the CDX API and obtained time maps for each of these URLs, not just homepage URL, but also URLs that are nested within, up to a depth of 2. Next, we dereferenced the mementos, downloaded their HTML and stored them onto disk. Next, we moved on to the data cleaning phase where we ignored mementos where the checksums did not match and ignored duplicates in order to make our results more consistent. By doing that, we ended up with a dataset of 90,977 records. We aggregated them into 2 datasets. So the first dataset, D0, contained only records of the home pages. The D2 dataset contained records of home pages and also the nested pages within that home page, up to a depth of 2, hence the name D2. Once we collected this data, we visualized how these captures were distributed over time. The figure shown on the right shows the distribution. We used the earliest capture time to sort these URLs, and you can see that there are several bands in time where the capture density was high. Since we wanted to analyze a large number of URLs and also needed to analyze captures that were dense in nature, we chose the time region between 2015 June to 2018 June as a period of study. So when we obtained some statistics of the data in this region, we saw that the median crawl interval of 80% of author home pages were between 20 to 127 days. Also, on average, an update occurred every 141.5 days for a home page and every 75 days for a website. The home pages changed less frequently than the actual website did. Next, we moved on to estimating the mean update frequency. So the method that we use to do so is based on a Poisson process. Based on this, we estimate a lambda value to see how likely a web page will be updated. However, the problem is that the data we obtained from the Internet Archive did not have a regular access interval. So for that reason, we used a maximum likelihood estimation for obtaining the lambda values. So here, TCI is the time duration between two consecutive updates, and TUJ, which is the time between a capture where an update was detected and a capture where an update was not detected. So we substituted these values into this equation and used Brent's method to numerically solve a value for lambda, which would be the maximum likelihood estimate for lambda. If you take a look at the figure on the right, these TC values fall between two consecutive updates. Here, the black color triangle represents a capture where an update was detected, and the white color triangle represents a capture where no updates were detected. So here, between two updates, we consider it as a TC or a change timestamp. And between an updated capture and an unupdated capture, we consider it as an unchanged time duration, which is TU. So here we examine a specific type of update, the addition of new links. We chose this definition to capture when authors add new publications into their pages. And also we use two methods to estimate these updates, which is what's shown on the top of this figure and the bottom of this figure. So in the top, the black and white triangles show the actual updates, the actual accesses. But the triangles on the bottom represent interpolated accesses. Realistically, you don't know at what point in time the web page actually changed between two captures. So for the sake of argument, white color circles represent a hypothetical update. So here, the gray color shade represents how far away we are from the actual update. So what we did in the second method was we got the midpoint between two captures as the interpolated update time. So as you can see below this timeline, the error is less than above timeline. Next, we moved on to validating our estimates. So here you can see on the left side, figure 5, the red color dots represent the mean interpolated update intervals, while the blue color dots represent the median interpolated update interval. So you can see a similar trend on both homepage level and website level. And on the figure 6, which is given on the right, we drew a Poisson distribution line and we plotted them together. For website level, the distribution of update intervals fall on top of this Poisson process distribution line. However, for home pages, there seems to be a difference in this trend when the interval is less. So this may be due to some weak correlations that exist between the update intervals. But for a majority of cases, this worked. So next, I define our prediction model. So here we used two functions, f and g, to perform our prediction. So the function f takes a set of captures as an input and outputs an estimated mean update frequency and the last known update time. for that capture. And the function g takes in a lambda and tau given out from the equation f here, and also a time interval e. And from those values, it provides a prediction of probability that a website changes after a time interval e since t. So we use these two equations to evaluate and get results for a simulated crawl scheduling task. The green color region represents the data that we use to estimate the lambda, and the yellow color region represents the data we used to evaluate our estimation on it. On the left-hand side, you see there were 4 URLs. We use that as the M value and get a prediction for the estimated mean update frequency. And from that estimate, we predict what's the probability that each URL would change on the t plus e time. And if that probability is high, then we schedule these URLs for crawl. If not, we do not schedule them. So ideally, if our model schedules U2, U3, and U4, it would be a perfect scheduling. So let's move on to the evaluation methods that we used. So here, the first evaluation we did was to try and see if we are selecting the right URLs. So we use 2 baseline models to do this. So the first model is a random selection where we select X random URLs, where X is the number of URLs that was selected by the HAX model. And the next baseline is a brute force one, where it selects all URLs for crawling, regardless of whether they change or not. Note that we get a probability output from our prediction model, but we have no way to select URLs out of those. Here, we use a thresholding parameter, theta, to define that cutoff region where you only select URLs having a probability greater than theta. And we did this evaluation at homepage level using the D0 dataset, and at website level using the D2 dataset. So this is the results that we obtained for a precision. So here, the blue color represents the highest value obtained under different averaging conditions. When we select the best theta value, our HAX model has the highest average precision. So the right-hand side figure shows how this precision value is distributed when theta changes from 0 to 1. At homepage level, when history size is 1 week, we can see that the HAX model has a high precision compared to the other 2 models, which basically lie flat. And the trend is kind of the same when history size is also 2 weeks. And at website level, there's not much of a prominent difference between the two. But still, the HAX model has a lead compared to the other models. So when we take a look at the results for the recall that we got, we see that the HAX model yielded a better recall than the random model when theta is optimized. If you take a look at the table here, you can see that the highest recall was obtained by the brute force model. Why this happens is because the brute force model selects all URLs, hence they have perfect recall. But ideally, we want to avoid that kind of scenario. We want to only select a subset of URLs in order to not waste time and bandwidth. When we compare with the random model, the HAX model has a consistently high recall for all values of theta, as you can see on the right-hand side figure. And it's the same for the homepage level. At the website level too, the recall value is high for a HAX model compared to the random model. Maybe not so high as the homepage model, but still an increase in recall. And if we take a look at the F1 score, the HAX model yields a higher F1 score than the baselines when theta is optimized. So if you take a look at the table, you can see that the highest values that we obtained was for the HAX model. But if we look at the distribution to the right, we can see that the HAX model and the random model have a similar distribution up to a higher value of theta. And then as theta increases For the homepage level, the F1 score keeps increasing, and it has a slight lead than the random model. And if you take a look at the history of 2 weeks for the homepage level, we have an increasing trend. And then for the micro average, it shows a drop beyond 0.6. But for the macro average, it keeps increasing. And if we take a look at the website level, we see that there is a maxima for the threshold for both sizes of history. And when we take different points of threshold values, we can observe that the HAX model has a higher F1 score than the random model for different values of theta. If you look at the brute force model, it just has a flat F1 score because it selects all URLs regardless of theta. So the second evaluation method that we used was whether we are prioritizing the URLs correctly. So here we use two baseline models. So the first model is last obs, which is the cross-scheduling model used by ScienceSeer. So in this model, URL ranks are determined by the date they were last accessed. So if you have a URL that has not been updated for a long time, then that URL is crawled first, and vice versa. In the random model, the URLs are ranked randomly. So in order to compare between these models, we used a mean weighted precision at K metric. And we performed this evaluation at both homepage level and website level. So here is the results that we obtained from this evaluation. So as you can see on the right-hand side figure, the HAX model has a higher mean weighted precision at K for both datasets, D0 and D2. How we obtained this mean weighted precision at K was we compared each URL ranking to the expected ranking. So we had precision at K values for different values of K, for different history sizes, and at different reference points in time. So we first calculated a weighted precision at K over the history size and reference point T by using a logarithmic decay function over different values of K. Next, we took T out of the equation by calculating the mean overall values of T. And in that way, we got one mean weighted precision at K for each history size. So this is what is shown on the figure on the right. So in the future, we will investigate different types of updates, such as the addition of a scholarly publication in PDF format. We'll also crawl author websites regularly to prevent missed updates and check its effect on the model performance. Remember, in Internet Archive, the access is very regular, but we want to evaluate whether having regular accesses will improve performance of a model. We also plan to generalize this work into other domains by exploring non-scholarly URLs. So in summary, we studied the problem of improving the efficiency of a focus crawl scheduler for the scholarly web and found that the estimated mean update frequencies follow a log normal distribution. And we used archive data to find and schedule a subset of seed URLs that are most likely to change before the next crawl. And we showed that our scheduler achieved better results than the other baselines when we select an optimal value for theta. So our code and data is available on GitHub in the following link. Thank you.